Hey folks, welcome back to Combo Class. Today I want to show you some really cool patterns that emerge when you take a number, you multiply its digits, then you take the result and you multiply the digits of that and you repeat the process. And first I'll show what happens in the typical base 10 system that you're used to writing numbers in. Then I'll show what would happen in a variety of other bases to show how these patterns reveal some really interesting things about numbers on the bigger scale. In this video, when I use the term number, assume that I mean 0, 1, 2, 3, etc., not any fractional or negative numbers. We're just looking at these ones called the non-negative integers today, and for now, assume that I'm referring to the typical base 10 way of writing these numbers, for example 12 having the digits 1, 2. Now to build up to multiplication, let me show you what happens when we add the digits of a number repeatedly. Let's say we add up the digits of a number, taking what's called its digit sum. If we do this to a single digit number, the result will be the same as itself, so the single digit numbers are known as fixed points under this operation, whereas if we take the digit sum of a multi-digit number, it'll shrink, meaning the result will be smaller than the original. And if we repeatedly take the digit sum of a number, it'll eventually shrink down to a single digit fixed point. Now, the persistence of a number under a given operation is the amount of times you'd have to repeat that operation starting from that number to reach a fixed point. And additive persistence refers to this with the operation of digit sums, where the additive persistence of a number is the amount of times we'd need to add the digits starting from that number to reach a single digit number. For example, the number 679 has additive persistence 2 because it takes 2 steps of adding the digits before it becomes a single digit number, and we only count the steps up to a single digit number because those are the fixed points that would stay at themselves if we took any more digit sums. Now, if we look at the record breakers, meaning the smallest numbers to have new larger levels of additive persistence, we'll notice a pattern. The smallest number with additive persistence 1 is the number 10, the smallest multi-digit number. The smallest number with additive persistence 2 is the number 19, which is the smallest number whose digits add up to a multi-digit number. And we can sort of backtrack, where the smallest number with additive persistence 3 is 199, which is the smallest number whose digits add up to 19, the previous record breaker. Now this pattern continues, but the resulting record breakers do get large pretty quickly. The smallest number with additive persistence 4 is just the smallest number whose digits add up to the previous record breaker 199. But to find a number whose digits add up to 199, you have to go beyond billions and trillions all the way up to this number, a 1 followed by 22 nines, which is the smallest number with additive persistence 4, and the next record breaker has way too many digits to write them all down. After the fourth record breaker had been a 1 followed by 22 of the digit 9, the fifth record breaker is a 1 followed by this many of the digit 9. There's literally not enough space on the planet Earth to write down all the digits in this number. Now, even if we counted our numbers in a different base, in any basic base like base 2, base 3, base 4, and so on, the record breakers of additive persistence would have a very similar pattern, where the first one would look like 1, 0, and then the rest would look like 1 followed by a string of the largest digit that exists in that base, with each record breaker being the digit sum of the next record breaker in a chain. And although this chain gets huge quickly, it is infinitely long, meaning this pattern continues forever and guarantees that in base 10 or any similar base, additive persistence can be arbitrarily large. And somewhere on the number line, there are numbers with additive persistence 1 billion or whatever level of additive persistence you want. But now let's go from addition to multiplication, where things become a bit more mysterious. Let's say we take the digits of a number, not including any unnecessary extra zeros after a decimal point or before the number, just the digits that are necessary to describe the number. And you can assume we're using typical base 10 digits until I specify otherwise. Now, instead of adding the digits, we're going to multiply them, taking what's called the digit product. If we do this to a single digit number, the product of a singular thing is technically itself, so single digit numbers lead to themselves and can be called the fixed points here here again, whereas if we take the digit product of a multi-digit number, it'll shrink, and if we repeatedly take the digit product, it'll eventually shrink down to a single-digit fixed point. So similar to how we looked at additive persistence, we can also look at a number's multiplicative persistence to count how many times you'd have to take a digit product starting from that number to reach a single-digit fixed point. For example, the number 39 has a multiplicative persistence of 3 because it takes 3 steps of applying a digit product for it to reach a single-digit number, and we only count up to the single-digit numbers because if we repeated the process, they would stay at themselves. Now here's what would happen to the first few multi-digit numbers if we took a repeated digit product, and the amount of arrows that each one takes is its multiplicative persistence. If we look at the record breakers, the smallest numbers to reach a given level of multiplicative persistence, first we'll find some more obvious cases, like the first multi-digit number, 10, is the first to take a step, and the first number whose digits multiply to a multi-digit number, which is 25 here, is the first to take 2 steps. But then the pattern becomes a little stranger looking, with 39 being the first to take 3 steps, and 77 being the first to take 4 steps. Here, we can't just backtrack as easily as we were able to with additive persistence because there are no set of digits that will multiply to 39 or 77. That would require us to have a digit 13 there or a digit 11 there, and so we have to find new chains. Although these record breakers aren't in a direct chain, you can start to notice something interesting in common with their appearances. The next record breaker is 679, and then next is 6,788, and then 68,889. And then our record breakers look like this, and then this, and then this, and then this. And I didn't run out of whiteboards, but this is the largest known level of record breaker in our base 10 system. In base 10, no number with multiplicative persistence 12 has ever been discovered, and it's unknown if any numbers with multiplicative persistence larger than 11 even exist. To understand some of the strange behavior that occurs when you repeatedly multiply the digits of the representations we're used to numbers having in the base 10 way of writing numbers, it helps to see what would happen with multiplying digits if we had written our numbers a bit differently, by looking at what happens with multiplicative persistence in some other bases. Now, you don't really need to understand other bases to follow along with the rest of this, but the basic details are that we're used to counting in base 10, where places in a number are worth values that correspond with powers of 10, and we could have places in a number correspond with powers of some other base number b instead. Here we're just going to be looking at what I call the basic bases, where b is a whole number larger than 1. And in base 10, there are digits for 0 through 9, but in general, there will be digits for 0 through 1 less than the base number b. Now let's look at multiplicative persistence in base 2. Base 2, also known as binary, is an interesting case here. The number 0 and the number 1 themselves are fixed points here, but what about larger numbers? Well, any whole number will have some string of zeros and ones that represents it in binary, and since 0 and 1 are the only digits we'll encounter in a representation here, we're either going to have a number that its representation has a 0 somewhere in it, which will multiply to 0, taking 1 step to reach that fixed point, or we'll have a number that's binary representation is just the digit 1, in which case it'll multiply directly to 1, the other fixed point. So regardless of which whole number we start with, it'll either be a fixed point or take just 1 step to become a fixed point. So base 2 has a maximum multiplicative persistence of 1. But now let's look at base 3, which is a bit different. In base 3, the single-digit fixed points are 0, 1, and 2, and the first multi-digit number 1, 0, which we know as 3, is the first number that takes one step. But here, there are some multi-digit numbers that can go a little further. The number 8, which may not seem like a multi-digit number to us in base 10, does have multiple digits in base 3, where it looks like 2, 2, and if we apply this process to it, we end up with 4, which we're used to writing that way. But then if we apply the process to 4, and write that in base 3, which would look like 1, 1, we need to take another step, multiplying those digits to actually get to one of these fixed points. So 8 is the smallest number with base 3 multiplicative persistence larger than 1, taking 2 steps. But what about more than 2 steps? Well, if we're just looking for numbers that have a record-breaking level of multiplicative persistence here, we don't want to check any numbers that contain the digit 0 anywhere in their representation, because those would get sent to the fixed point 0 after a single step. And we also don't need to check any numbers that contain the digit 1 anywhere in their representation, because times 1 won't change a digit product. So if we removed those ones, we'd get a number that was smaller but had the exact same multiplicative persistence. So if we're just looking for examples of whether a number can take 3 steps or 4 steps or more, we only need to look at the numbers whose base 3 representations don't have any zeros or any ones. In other words, are just some amount of 2's in a row. These contenders, which look like strings of 2 in base 3, are the numbers that are 1 less than a power of 3. And because their first digit product in this base will be a bunch of 2's multiplied together, that'll result in a power of 2. So the second time we take a digit product starting from one of these contenders, we'll be multiplying the digits of how some power of 2 looks in base 3. For example, the first number with a multiplicative persistence of 3 in this base is the number we know as 26, which looks like 222 here, and that leads to 2 to the third power as the first digit product. 2 to the third power looks like 22 here, and as we saw, 22 takes 2 steps here, so 222 takes 3 steps here. But with a string of 4 2's, that leads to 2 to the fourth power, which looks like 121 here, which is small enough it goes straight to the fixed point 2 on the second step. And with a string of 5 2's, we encounter a different issue. After one step, it looks like 1012, which goes straight to the fixed point 0 on the second step, simply because any digit string containing a 0 will get sent to 0. So for a number to have multiplicative persistence of more than 2 in this base, it needs to be a string of 2's that leads to a power of 2 that contains more than one of the digit 2 to get further than a fixed point, and more crucially, doesn't contain any of the digit 0. And if you look at how the powers of 2 look in base 3, you'll notice that after 2 to the fourth power, they all seem to contain zeros, making their associated contender numbers crash to a fixed point after the second step. This boils down to the question of whether any further powers of 2 have a zero-less base 3 representation. You will find one surprising case where 2 to the 15th power doesn't contain any zeros, so a string of 15 2's doesn't go to the fixed point 0 right after the second step. It goes to 2 to the 6th power. However, 2 to the 6th power does then go to 0 after one more step, so that's just another example of multiplicative persistence 3. To get past persistence 2, a number has to dodge zeros in the right lucky-seeming way, not only once, but once for each further persistence level it has any chance of reaching. Now, zero-less, also known as Zerofree numbers, play such a big role in this topic that I'm going to take a moment right now to explain a few things about them. Zerofree numbers get proportionally rarer as you go up the number line, but different sorts of sequences will or won't contain them to different degrees. For example, the numbers that are 1 less than powers of 10 when written in base 10 are just strings of 9s with no zeros in sight. But if we have a sequence like the factorials, where you multiply all the whole numbers up to some point, those, after a certain point, are guaranteed to contain zeros. But some sequences don't have as simple of a digit pattern as those examples, and there's a chance that with the powers of 2, it's sort of like a statistical game. And here let me make a little analogy to try to make that aspect feel a bit more intuitive. Let's say you had a random 1 in 10 chance of winning some prize, but if you failed, you got to try again with a 1 out of 100 chance, and if you failed that, you got to try again with a 1 out of 1,000 chance, and then with further powers of 10, well, the chance of winning a prize overall would be 1/10 plus 1/100th plus 1/1000th plus etc. up to the point you stop playing, and even if you continue that series infinitely, it'll never add up to more than 1/9. So even if you try this game infinitely many times, you'd be more likely to never win a prize than to win at some point. Although the exact statistics are different, if the digits in the powers of 2 expressed in base 3 turn out to always behave as randomly as it appears, finding a zero-free power of 2 larger than 2 to the 15th power might be something like that prize, where even an infinite amount of chances at hitting it still gives less than a 50% chance it'll ever occur. And although there was that surprise with 2 to the 15th power, when you look at powers of 2 expressed in base 3 beyond that, it does seem like they all contain zeros. As you go along in a sequence like this, it becomes less and less likely that you'll encounter a term where all of its digits are able to dodge the digit 0. And unless there's some secret pattern hiding in the powers of 2 expressed in base 3 that mathematics is not aware of yet, statistically, it's very likely that all powers of 2 beyond 2 to the 15th power have at least 1 0, so it's conjectured that base 3 has a maximum multiplicative persistence of 3, and that the only numbers that reach that maximum are the numbers whose representations in base 3 are either a string of 3 2s, a string of 15 2s, or one of those with any amount of the digit 1 mixed in. But there are still many open questions about which representations of numbers are zero-free, and mathematicians have not been able to prove that conjecture yet. Now, the powers of 2 are only so notable here within base 3, and when we look at larger bases, we'll find different families of numbers that turn out to be extra notable. But in base 4, there is a pattern that's relatively similar to that pattern right there. In base 4, the single-digit fixed points are 0, 1, 2, and 3. Once again, the first record breaker is just the smallest multi-digit number in the base, and the second record breaker is the smallest number whose digits multiply to a multi-digit number in the base. Similar to before, are record breakers that take more than just a single step would not involve a digit 0, that would make them crash to 0 too quickly, or a digit 1, because that would be a trivial digit that could have been removed to have the exact same product. But here we also meet the fact that if we have more than one of the digit 2 in base 4, like with a number that would look like 223 in this base, the product is guaranteed to have a 0 at the end, because 2 times 2 equals the base number, and so that could last a maximum of 2 steps. So if we wanted numbers that went more than 2 steps with a multiplicative persistence of 3 or more in this base, not only would the record breakers not have a 0 or 1, but they also would have only up to a single 2. Essentially, they would only have the digit 3 along with up to 1 2 in the mix. Now, the number we know as 63, which looks like 333 in base 4, manages to make it 3 steps. But after that, no numbers have been discovered that make it 4 steps. If you imagine multiplying the digits of a number of one of these forms, you'll see that the record-breaking contenders will all have their first digit product result in either a power of 3 or exactly twice a power of 3 expressed in base 4. And similar to the powers of 2 in base 3 that we looked at, it seems highly likely that beyond the large range that mathematicians have already checked here, all further powers of 3 and numbers that are twice powers of 3 when expressed in base 4 contain zeros, but although it's statistically likely that all numbers of this form after a certain point contain zeros, that hasn't been proven. And so, like in base 3, there's an unproven conjecture that base 4 has a maximum multiplicative persistence of 3. Now, beyond base 4, things get a bit more complicated. In base 5, we can notice some of the same patterns as before, like single-digit numbers are the fixed points, record breakers of persistence more than 1 won't contain the digits 0 or 1, and the first 2 record breakers are simply the first multi-digit number and the first number with a multi-digit product, and those are patterns that'll continue with further bases. But here there's a different twist on something we saw in base 4. In base 4, numbers that contained 2 of the digit 2 couldn't be a record breaker beyond the second step because that pair of 2's would multiply into the base number and make a 0. Now in base 5, a record breaker also won't contain a pair of 2's, but for a different reason. Remember how the digit 1 can be removed to still have the same digit product, so it won't show up in our record breakers after the first one? Well, similar to that, in base 5 and above, a pair of the digit 2 could be replaced with a single 4 to get a smaller number with the same digit product. So here we won't see more than one of the digit 2 in one of these record breakers because 2 can be replaced with 4. Now that leaves numbers with up to 1 of the digit 2 and then some amount of the digit 3 and or some amount of the digit 4. Let's also note another pattern, which applies to every basic base, but you can only start to notice it at around base 4 or 5. Any 2 numbers, which are composed of the same multi-set of digits, just in a different order, will have the same digit product, and thus the same persistence in that base, so only the smaller of those numbers could potentially be the first number to reach a new level of persistence. So apart from the first record breaker, which always looks like 1, 0, any record breakers in a given base will need to have their digits in non-descending order, meaning that the representation in that base will start with the smallest digit, and then each following digit will be at least as large as the previous digit. Altogether, the base 5 contender numbers for record-breaking levels of persistence beyond the second level must have one of these specific forms, which means that their first digit product must have one of these forms. Now, here are some record breakers in base 5, and although this base has a larger amount of different families that the record breakers can come in, we do encounter something similar, where there appears to be a limit of multiplicative persistence, although here it seems to be all the way up at 6. So far, we've seen each new larger base get at least as far with its conjectured maximum as any smaller base, but that isn't always the case. With base 5, we got up to multiplicative persistence 6, but in base 6, the conjectured maximum is only persistence 5. This relates to the fact that 6 is a very divisible number while 5 isn't. It's a prime number. Although base 5 could have record breakers containing both the digit 2 and the digit 3, any number containing a 2 and a 3 in base 6 will have those digits multiply to the base number 6, leading to the product ending in a 0 and the product of the product being 0, making that number have a maximum multiplicative persistence of 2. So there are more combinations of digits that need to be avoided with highly divisible base numbers. In general, the different bases that have been investigated in this way each have a conjectured, but not proven apart from the case of base 2, maximum multiplicative persistence. And as we go higher, sometimes by having a larger base number, it seems like there is a larger maximum. Like in base 7, simply from having more symbols that could potentially be part of a record breaker, and from being a prime number that's not very divisible, there's numbers all the way up to multiplicative persistence 8. Whereas in base 8, despite that being bigger, for some other reasons, such as it being more divisible, there only seems to be numbers up to multiplicative persistence 6. Now let's jump back to base 10 for a bit. At this point, if we combine all the patterns I showed with smaller bases, we can deduce what the patterns should be in base 10 to help explain things like its list of record breakers. In base 10, the fixed points and the first 2 record breakers have the exact same pattern as in the smaller bases, and with record breakers beyond that, things aren't identical to before, but they do follow similar types of patterns. In particular, the contender forms for record breakers of persistence more than 2 have a couple notable types of restrictions that we saw simpler versions of earlier. First, we can't have things that cause the digit 0 too quickly. Obviously, that includes the digit 0 itself, but also other combinations of digits. Like, remember in base 4, we couldn't have 2 of the digit 2 because the product of a pair of 2's is a multiple of the base number, and that causes a 0 on the second step. Well, the base 10 version of that is, we can't have both the digit 5 and a digit that is even, because 5, along with any of 2, 4, 6, or 8, would cause a 0 too quickly. Like before, these record breakers also can't include the digit 1, and here, let's think of removing a digit 1 as replacing a digit 1 with an empty set of digits, because this connects that pattern to the other main type of digit pattern that must be avoided with these record breakers, which is any digit combo that could be replaced by something else and have the same digit product but end up being a smaller number. Like, remember in base 5, we couldn't have 2 of the digit 2, and that time it was because a pair of 2's could be replaced with a single 4 to make a smaller number with the same product. And that turns out to be true in any base that the digit 4 fits in. Now, unlike the 0 dodging restriction, which relied on the number's factors, this type of restriction just relies on the number's size, and the digit combos that are inefficient for any base also will be inefficient for larger bases, like 2, 3 could be replaced by 6 in base 7 or any base larger than 7, and won't show up as a record breaker in any of those. So by base 10, we've already stacked a bunch of digit combos that couldn't possibly be in a record breaker of persistence more than 2. Any of the digit 1 could be replaced with nothing by removing them. Any pair of the digit 2 could be replaced with a single 4. Any 2 and a 3 could be replaced with a 6. Any 2 and a 4 could be replaced with an 8. Any pair of 3's could be replaced with a 9. And then we get to some sneakier ones where we're replacing something with the same amount of digits, but which will still result in a smaller number. Like a number with a 3 and a 4 in it could have those replaced with a 2 and a 6. A 3 and a 6 could be replaced with a 2 and a 9. A pair of 4's could be replaced with a 2 and an 8. A 4 and a 6 could be replaced with a 3 and an 8. And a pair of 6's could be replaced with a 4 and a 9. With all of these restrictions occurring at once, it's not really a surprise that the record breakers look similar to each other. In base 10, when you combine all these restrictions, you can deduce that any record breaker of persistence more than 2 would have to be one of these precise forms. We can see these forms in the 3rd through 11th record breaker, and if a 12th record breaker does exist, it would also have to be one of these forms. So mathematicians are able to test really large ranges of numbers by just focusing on these specific families. Over time, more and more numbers have been checked in this way, and by now, in base 10, all the contenders that have up to 30,000 digits have been checked, which means that if there is a number of multiplicative persistence more than 11 in base 10, it would need to have more than 30,000 digits. And larger stretches of number line will probably be checked over time, but checking finite sections of an infinite number line won't add up to a proof. Theoretically, maybe someday somebody will find a clever way to prove that no counterexample of this sort exists. Such a proof would probably relate to proving that each of these families of number has a point on the number line where it always contains zeros afterward. For now, our best guesses are based on statistical probabilities for how these families of numbers should have their digits behave beyond the size that's already been checked, and that ends up similar to that game I mentioned back in base 3, where it seems almost impossible that a number could dodge enough zeros, but although the statistics show that it's almost 0% that will happen, we aren't positive that these statistics accurately will apply, because these statistical probabilities rely on assumptions about the degree to which the digits in certain families of numbers act random. They won't be literally random, but even if they are anywhere remotely close to how a random digit distribution would behave, then these statistics will still point toward the conjectures being extremely likely to be true. However, it's hard to be sure that none of these families of number have some sort of hidden pattern and that their digits really do behave in a random-like way. To the best of what mathematics currently knows, though, these statistics are probably accurate, and if the statistics do turn out to be right, then persistence not only stops there, it actually, in some ways, shrinks. You see, in base 10, for example, you can always make a new number of whatever persistence up to 11 that you want by taking a number you already know that has that persistence, putting its digits in whatever order, and then adding some more of the digit 1. However, if you ignore numbers that are mostly just the digit 1, like let's say we only analyzed numbers with a unique set of non-1 digits, well, we'd find that small numbers can't get very far with their persistence, and then with larger-ish numbers, they can go further with persistence, but then with even larger numbers, they can't again. Like in base 10, this is the largest known number with persistence 11 that doesn't contain the digit 1. And it's not just persistence of 11 that seems to lose its abilities. It looks like as you go up the number line, you get to a point where unless a number is almost entirely the digit 1, with just a small handful of non-1 digits that are a rearranged version of something we've met before, a number can't have multiplicative persistence more than 2. None of this has been proven. However, from what the empirical data seems to hint at, this not only seems to be very likely for base 10, but seems to be likely for the other basic bases as well. Each base seems to build up towards some maximum persistence, then sort of freeze, and have its non-trivial possibilities shrink back down to level 2. As we get to larger and larger numbers, in base 10 or another of these bases, we'll find that more and more numbers contain the digit 0, and even the numbers that don't often have a product that contains the digit 0. So if you look at a large number that isn't just a rearrangement of the digits of a previous record breaker with some extra ones thrown in, it's very hard to find a large number with multiplicative persistence more than 2. So it's conjectured that in every basic base, every persistence level larger than 2 has some point where it ends up only being achievable in this trivial way with numbers that already were that persistence with another 1 attached. If this conjecture is true, there are all sorts of interesting lists that could be made of reverse record breakers that are not the first number to do something, but the last number to do something, like the last one-less number to reach a given persistence level in a given base. Now, when we start comparing various bases together, we'll also find some other strange similarities and differences, and that's not the end of the surprises and mysteries here. Here are some diagrams from a notable paper that was released a few years ago by the mathematician T. Lamont Smith, and these tables show more lists of all the known record breakers from base 3 all the way up through base 24. The left column on each of these is a persistence level, and the right column is the smallest number to reach that in the base, written in the language of the base itself. So for bases larger than base 10, we need more symbols. A means a digit worth 10, B is a digit worth 11, and so on. This is a lot of amazing data, but some of the patterns here can be a little more clear if we find ways to compress all these bases into a single table or sequence. Like if we made a list that counts how many terms are in each of these different tables, we would get the sequence of conjectured maximums in different bases, which I showed the beginning of earlier, and now let's look a little further at that sequence. The data I'm going to show here is from the OEIS, the Online Encyclopedia of Integer Sequences, which is the best resource to find this type of sequence, and here it fits extra well because the creator of the OEIS, Neil Sloan, was also the first mathematician to write about and formally study multiplicative persistence. Looking further through what's currently known here, we can see that larger base numbers do often have a larger result, although it's still not been proven that the overall trajectory of this rises upward on the big scale. Sometimes the numbers here hop downward where a larger base has a smaller result, often when the base number's very divisible, but seemingly also related to some other unknown traits. Unfortunately, this list of conjectured maximums only goes up to base 24. Beyond that, not enough has been calculated yet about larger bases to make a confident conjecture for any of them. It's hard to make guesses about where this is going when it has a limited number of terms. We don't even know if those terms are correct. And in fact, we don't know whether they're correct to such a degree that we don't even know if every base actually has a finite maximum. It's extremely likely, but hasn't been proven. Theoretically, this sequence might not even be an integer sequence, because some of the results here would basically be infinity. Currently, there's not really a possible way to verify the terms without some sort of new proof, because you can't confirm them with some finite amount of data. However, there is another sequence with a really similar way of defining it, which is sort of like viewing this from an alternate angle, and this next sequence could have any individual term calculated just from some finite amount of data. That last sequence showed the conjectured maximum persistences that any possible number within some specific base could have. What if we flipped those last two and instead listed maximum persistences that any base could have when talking about a specific number? Well, a number will have persistence 0 in any base larger than its own size, So for a given number, you'd only need to check a finite amount of bases between 2 and right under itself to know all of the distinct, different persistences it has. Then you could look for traits such as the maximum of those. For example, the number 8 has a maximum multiplicative persistence of 2, which it has in base 3, and in all other bases it has a smaller multiplicative persistence, and the maximum multiplicative persistence a number has in any basic base altogether is sometimes called that number's absolute multiplicative persistence. And let's look at a sequence of some of these results. This sequence has way smaller terms than the last sequence, but each term is way easier to calculate, so this list is way longer. And looking through it, we can see that it definitely seems to be ascending over time, and not just with its average, but it seems to have a rising minimum, like there's some floor that's increasing, where after certain points, the result must be at least as large as some size. This leads to many interesting conjectures. For example, from what it seems, numbers larger than 12 always have at least one base where they have a multiplicative persistence larger than 1. If that's true, then these circled numbers are the only numbers with a result of 1 here. Conjectures like that relate to unsolved questions about the final time a number appears as a result here, but we could also look at the first time a number appears as a result. That would be like the record breakers of this sequence, which can be seen as this sequence here, with the definition that the nth term is the smallest number that has persistence n among any of its basic base representations. To me, this is like a more fair version of the more popular list of base 10 record breakers, because it's more base neutral. Although here the results are written in base 10, and some of these sequences could also provide other insights if they were written in other bases. There are many ways we could describe one of these sequences, and in a way, the last few sequences are describing the same mysterious array of information about specific numbers, bases, and persistence levels, just from alternate angles. These different angles all capture their own unique sorts of patterns and mysteries, but they all encounter the same types of problems with the digits 0 and 1. And while the digit 1 causes some anomalies, we found ways to ignore it and still look at the patterns beyond it. And those patterns beyond it are often caused by digits larger than 1 doing interesting things that we only get to see the very beginning of, because whatever pattern starts forming ends up getting cut short by zeros. And we can't just ignore zeros the way we ignored ones. When a single zero shows up, it obliterates any other patterns that were in process. But when I say we can't ignore zeros, that's just because of how multiplicative persistence is typically defined. When we're playing around with numbers, we can make the rules whatever we want. 0 is an amazing number, but sometimes can be too powerful and need to be excluded from some realms. This happens in common aspects of math, like how you can't divide by 0, and it also already happened within this episode related to multiplicative persistence. When I first mentioned digit products, I had to clarify that we don't want to attach any leading zeros or trailing zeros to just not include them. So we've already kicked out 2 types of zeros. Why not try kicking out a third? What if we just ignored them all and treated our digit products as non-zero digit products? Or equivalently, we could turn all the zeros into ones. This has been studied to a degree. It's sometimes called the Erdős variation of multiplicative persistence, after the mathematician Paul Erdős, and it has gotten some developments over the years, but as usual, mostly just in base 10. So here I just have some base 10 related details to show, but even just those are very interesting. If we look at record breakers for this alternate type of multiplicative persistence and compare them to the normal record breakers, the first 10 record breakers of each type are exactly the same. And then the 11th one is different. Then, as you know, the normal type of multiplicative persistence seems to stop there, but this other variation doesn't. In this other version, we do meet numbers with persistence 12 and 13, and as you can see here, apart from the fact that the 11th record breaker of each is different, it would almost look like this alternate sequence is just some sort of continuation of the other. And the record breakers of persistences all the way up through 20 in this alternate version are known. Here are some notes on the OEIS that describe them in a different form. They have too many digits to write in the normal way like the first 13. And here's the rest of those notes where we can see that there are also 19 more conjectured terms. We can also see that this list is conjectured to be infinite. In a way, it's like an opposite version of the conjecture there is about the normal type of multiplicative persistence, which is conjectured to be finite. When I first heard about this variation, and then thought about it for a while before I ended up finding this list, the results on this list were sort of exactly what I'd been hoping for. This list is a minuscule sample size, but if it does hint anything, it seems to be a clue that alternate zero-skipping versions of other bases or angles might also go further than normal while still keeping the patterns similar. Earlier I showed additive persistence, which does have limitless persistence levels, but which just isn't as mysterious or interesting as multiplicative persistence. And if this variation had a bit of each of those traits, that would be pretty awesome. Overall, with all these ways to look at multiplicative persistence, all the open questions and incomplete data, I feel like it's still a very underexplored realm, and that investigating deeper into the non-base 10 parts of this could have a quicker than usual success rate in terms of how long it might take to discover new things. And not only would I love to see more computational research about some of this, I also would love to see more casual explanations and descriptions of the patterns and connections you can see in the data. The concept of repeated digit products is extremely simple, and the type of thing that many people could find interesting and understandable if it was described to them in the right way, but most people would never discover all of its cool corners because they're not going to read through giant chunks of data and analyze the implications themselves. So I hope this video helped make more parts of this topic understandable to everybody, and hopefully showed more people that when something related to digits comes up, you'll find cooler things if you treat it as a whole array of different bases and not always default to the base you happen to count in. Anyway, there were some other clips with this door I filmed, but some of that ended up going badly, so I'll save that for a different video. And as far as this video, I filmed all of this, edited all of it, I even made all of the music in the soundtrack, so I hope you folks enjoyed. If you do like my videos, make sure that you're not only subscribed to this main channel, but also my bonus Demotro channel, where I put out some extra content in between these main episodes. And if you really like my videos, maybe consider supporting them in one of these ways, like some of these awesome folks. And I hope all of you watching this enjoyed the video and learned some interesting things.